Hi, welcome to my channel, JaberTime. Today I'm going to go over partial fractions, and I do have, as you could see from the screen, 5 examples. Let's get started. Partial fractions. As an introduction, imagine if you have these two fractions and you want to subtract them. Well, of course, you need a common denominator. In this case, since the denominators are different, we could just multiply them. So the common denominator will be x minus 1 times x plus 2. Doing the math right here, we're going to end up with 2 times x plus 2 minus 1 times x minus 1. Simplify, and I end up with x plus 5 over x to the second plus x minus 2. You could see it right here. 2 times x is 2x, minus x, that's just 1x. 2 times 2 is 4, minus 1, that's plus 1, gives us 5. So, as an introduction, if you are given this fraction and you want to integrate this quotient right here, when you want to integrate this, knowing this introduction example, I could split this fraction into 2 fractions. Then after that it becomes straightforward using the u substitution and len. The integration of du over u is len u. So we could take the 2 outside, and integrating 1 over x minus 1 will be len absolute value of x minus 1. Same thing right here. Here's the minus, and the integration of this part will be len absolute value of x plus 2. And of course, we don't want to forget the constant of integration. Now, in case the polynomial p of x on top has a higher degree than q of x, or even similar, like not less than. So if the degree on top is n and the degree right here is m, and we have the degree of p, which is n, greater than or equal to the degree of q. So n is greater than or equal to m. Then we use long division, and we end up with the following. We end up with the answer here, or the quotient, plus some remainder. This remainder has to be less than in degree than the degree of q of x. That's why it's called remainder. Here's example number 1. Notice that n is 3 and m is 1. By long division, we get the following. I'm trying to save you some time and write it down, as you could see. Writing this step by step on the whiteboard will take a way longer than the way I'm doing it. I just want to go over notes in less time, or lectures. So just to verify this long division, you take x cubed, divide by x, the leading term by the leading term, you get x to the second times x, and x to the second times minus 1. You get this, change signs and add them, this will cancel, and this will end up with the x to the second, and you just keep repeating. So this is the remainder. So the fraction inside is actually the following in a different format. Our quotient right here, x to the second plus x plus 2, plus the remainder 2 out of x minus 1. So to integrate this, it's like integrating these 2 parts. Integrating this will be straightforward, and integrating this will be just take the 2 out and len x minus 1 absolute value, of course. Don't forget the constant of integration. Case 1. Case 1, we have if q of x is a product of distinct linear factors. They're all linear first degree, and they're all different. This is in general. So if q of x, the denominator, is a product of distinct linear factors, then there exist constants, one for each, a sub 1, a sub 2, all the way to a sub k, such that we could write p of x over q of x as a sub 1 over the first factor, the linear factor, plus a sub 2 over all the way to a sub k over a sub k x plus b sub k. Of course, this a is different than this a. We're using different sized letters. Example number 2. The degree on top is less than the degree at the bottom side. And let's look at the bottom side, what we could do. The degree of p is 2. The degree of q of x is 3. So we don't need to divide. Let's factor the denominator. To factor the denominator, q of x, which is 2x cubed plus 3x to the second minus 2x, we could pull 1x out to get started. Now we have 2x to the second plus 3x minus 2, which could be factored to the following. Notice 2 times negative 1 is negative 2, and I have x times 2x, 2x to the second, in and out will combine to 3x. Let's take a look. 4x, that's 2x times 2, minus 1x, 3x. Now, as you can see, we have distinct linear factors for q of x. Since q of x has 3 distinct linear factors, the partial fraction decomposition of the integrand has the form as the following. Here we go. We're going to write 3 fractions. Each denominator will be coming from these 3 factors. And we have, instead of saying a sub 1, a sub 2, a sub 3, for the convenience, I'm using a and b and c. Now, solving this, trying to find a and b and c, we could combine this. Forgot here the plus sign. There's a plus sign. Combining these 3 fractions and compare it to the first original fraction, we could identify what's a and what's b and what's c. Here's the plus sign, shows up right here, as you can see. The common denominator will be the product of this factor and this factor and this factor, as you could see right here. This one is missing these 2. We'll bring them in. This one, this denominator is missing x and missing x plus 1. As you can see, I brought x from the left and x plus 2 from the right. This right here is available, but this one is missing and this one is missing. So we bring 2x minus 1 and we bring x next to x plus 2. Now if you bring x and 2x minus 1 to the bottom, you have to bring it to the top. Anything you bring down, you bring it on top to stay consistent and do it right. Next, let's open a new page and show you the math. So now we have the following, and I wrote this next to it. To combine these 3 fractions, having the same denominator, as you could see, we're going to end up comparing the numerator to the numerator right here, because that's going to be one fraction with this denominator, and the numerator will be adding this to this to this. Meaning, x to the second plus 2x minus 1, that's the numerator right here on the left. And the new numerator right here, after you combine them, will be a times this plus b times x and x plus 2, as you could see, plus c times x and 2x minus 1. Rearranging everything to see the coefficient of x to the second, the coefficient of x, and the constants together to compare it to this right here on the left. After rearranging, I could see that 2x times x, which is 2x to the second, and I have a, that's 2x to the second times a, and so on. B will give you bx to the second, b times x to the second, and x times 2x times c is 2c times x to the second. Moving on, I'm just gonna skip reading this. You know exactly what I'm doing. I'm just like multiplying using the distributive property and grouping all the terms with x to the second, and grouping all the terms with x and leaving the constant by itself. It's going to come from the first one right here. This will have an x, this will have an x, but when you multiply 2 times -1, that's -2 times a shows at the end. Now, the coefficient for x to the second is 1. The coefficient for x to the second is this right here. That will be the first equation. Second equation will be this, should equal to 2. And the constant should equal to our constant on the left, which is -1. -2a should equal to -1. Using algebra steps, elimination and substitution, we get a equals 1/2 and b equals 1/5 and c equals -1/10. Of course, the algebra steps here are skipped just for the convenience of saving time from the video. But there is a shortcut. It takes some steps and some time to find these guys right here, which I'm skipping, and I'm sure you could follow that or do it yourself, verify. But there is another way that you might appreciate and like. Alternative method to find a, b, and c. Now, I wrote everything right here again and again 3 times. We're going to do the following. I could see that on the right side, there's some certain numbers that will simplify my calculations. For example, let's go back. For example, if I plug in 0 here, this whole thing will cancel, no matter what this will give me. And that will cancel. So 0 is a good choice to simplify. So what's left will be some numbers here and a -1 on the left. Same thing here. Look at this one. If I plug in, let's say, -2, the whole thing right here will be 0. That will be 0. Everything here, 0 and 0. Finally, from this part, I could plug in 1/2. So let's start with zeros. Every x will be replaced with 0. That will cancel everything. That will force everything to be 0. That's a 0. That's 0. The only thing left is like right here. That's a 2 plus 0, which is 2. And that's a -1 because 0 minus 1 times a. So I'll have -1 from the left equals -2a. Simplify, divide by -2, divide by 2, a equals 1/2. Done. Second choice, let's plug in half right here. 2 times half is 1. 1 minus 1 is 0. This will cancel. And I have it here. That will cancel or will be 0 times. So this right here will go away. This here will go away. And the rest is just simple math. Every x will be replaced with 1/2. That will simplify to the following. 1/4 equals 5/4 b. Multiply both sides by 4. I get b equals 1/5. Finally, let's do what we did not try again. It's the -2. Putting -2 right here, that will cancel this. I will force it to be 0. That will force this to be 0. So I'll just have to deal with that. -2 here, -2 here, and everywhere x's. That will give me -1 equals 10c, or differently, c equals -10. So that's a good shortcut. That's another reason why I skipped the algebra from the previous slide. Next. So we had this problem and we factored the denominator to these 3 distinct linear factors. With the case 1 idea, we have a1, a2, a3, or in short abc, with a plus sign, of course. We came up with a to be 1/2, b to be 1/5, and c to be -1/10. Integrating this is so simple, just using the len, and you should be fine. just separate the integration of 1 over x ln x. After you take the 1/2 out, after you take the 1/5 out, use u substitution. You're missing a 2 here, so it's going to balance out with 1/2 outside, which forces 1/10 to show up, and so on. Since we have c in our calculations earlier, ABC, we don't want to write c here as a constant of integration, so we used a different letter like k. Let's go to case 2. If q of x is a product of linear factors, some of which are repeated. What does that mean? So notice that a1x plus b1 repeats enough times, but let's say it repeats twice. So if it repeats twice, we're gonna say a1x plus b1 to the second, and we use another fraction and another letter a1, a2, and so on. For example, to explain it, x is repeated twice and x minus 1 is repeated 3 times. So we write x, then we take it up to the second level, x is second, and we use a and b, or a1 and a2. X minus 1 to the third, we use x minus 1 to the first, then x minus 1 to the second, then x minus 1 to the third, and you could use other letters, but a, b, c, d, e is totally fine. Here's example number 3. We have a 4th degree on top, and we have a third degree at the bottom side. So what we have is an improper fraction, with long division being saved from written and going over it step by step. We end up with the following. This is the quotient, and this is the remainder 4x out of what we have in the denominator, x to the third minus x to the second minus x plus 1. Now, integrating this is the same like integrating this, but this one is done. That's straightforward. And to integrate this, we need to factor the denominator. So this is our q of x now, the new q of x. Since q of 1 is 0, we know that x minus 1 is a factor. As you could see, 1 to the third minus 1 to the second minus 1 plus 1. It's like 1 minus 1 minus 1 plus 1. That's 1. And the first one cancels to the other minus 2. So 1 and 1, I mean 2, which cancels this minus 1 and this minus 1. Then, to get started and factor it, we could rewrite this as x minus 1 as one factor, and the rest will be this, or divide this by x minus 1 to get the rest, and that becomes x to the second minus 1. Next, that's a difference of 2 squares, so I'm going to end up with x minus 1 and x plus 1. Combining these two, that will be x minus 1 to the second and x plus 1. Now we could see that we have a repeated factor. Let's go back to the problem. Let's go back to this fraction and take care of it. Now 4x over x cubed minus x to the second minus x plus 1 is now in this form. Using case 2 concept, we're going to write x minus 1 and write another fraction with x minus 1 to the second. As you could see, this one is once, we put it once. Same like before, we're going to combine these fractions and compare the numerator, the lengthy one, with 4x, skipping the steps, rearranging and solving, or using the alternative method. The alternative method will be by plugging 1, because that's going to cancel this one, once everywhere, and plug a negative 1, which is going to cancel this one and this one, and the third option by plugging in 0. With that, we're going to get x equals 1. After you plug in 1 right here and 1 right here, that's going to cancel. We end up with b equals 2. You could double check before I move on. Take a look. Plug in 1. That's going to cancel. So this whole thing will cancel. This whole thing will cancel. What we have on the right is only the middle term, and we have this. 4 times 1 is 4. 1 plus 1 is 2. 2b equals 4. So b has to equal 2. With the same concept, plug in -1 to cancel this term. We end up with c equals -1. And finally, plug in 0. We'll end up with a equals 1. Going back to the problem, and we have the following. Now earlier we had this on the side and a fraction right here with the idea of remainder, which we did find a and b and c. Now it's clean. Applying the integration to every term and thinking about len to use. Looking at this one right here, we're gonna take it to the side and take care of it. Let's take the second or the third term, from the remainder when we divided outside, 1 over x minus 1 to the second. So taking care of that on the side, we'll have the following. We could use u substitution, because if I multiply this by itself, that's going to be a polynomial of second degree, which is kind of hard to integrate because the top part is just 1. It doesn't have x's. So we take x minus 1 while it's inside as u, and du will be 1 dx. So that's like 1 over u to the second du, which you could use it as a power rule. Bring u to the second to the top to make it to the power -2, and integrate this normally. Add 1, that makes it u to the power -1, divide by -1, simplify it, and take it back to x. Instead of u, write x minus 1. So that's the integration of this part. Of course, we don't want to forget the 2. Going back, x plus 1 will give you x to the second over 2 plus 1 times x. This right here will give you a len. I have the 2 and the minus came. That's a -2. And the integration, this is integration already done, as 1 over x minus 1 minus len x plus 1, absolute value to be on the safe side, plus some constant, let's call it k, since a and b and c were used in the problem. We can't use c again here. Okay, next. We could combine len x minus 1 minus len x plus 1, which is some of the len or log properties, and make it 1 len with a fraction or a quotient. Len a minus len b equals len a over b. So we could put it as 1. You don't have to, but that's an option. Combining these two. That should do it. Case number 3. Let's see what we have. Case number 3. Q of x contains irreducible quadratic factors, none of which is repeated. So case number 1 was linear, distinct. Case number 2 was linear and repeated. Here we have quadratic and non-repeated. So we have of this form, ax plus b over ax squared plus bx plus c. For example, the q of x is irreducible. You can't reduce it or simplify it. And we have factors that this cannot be reduced, this cannot be reduced, this cannot be reduced, and they are all non-repeated factors and non-reducible. So To decompose this fraction and write it as 3 fractions, we will start with a over x minus 2. For this one here, it's a second degree, so we write a first degree on top, bx plus c. That's another second degree, x to the second plus 4. We write a linear on top, which is dx plus e, to distinguish from bx plus c. Sometimes we need to complete the square in ax squared plus bx plus c, and we use the following formula. Let me show you. This is one of the formulas that we use in trig integration. The integration of dx over x to the second plus a to the second will be 1 over a, that's this a, tan inverse x over a plus the constant c. Here's example number 4. So the denominator is x cubed plus 4x. Let's take it to the side. X cubed plus 4x. Take x out as a common factor. And now this part right here can't be factored further than this. It's irreducible. So what do we have now? Our fraction inside our function will be written this way. A over x, that's this linear part, plus bx plus c over this quadratic factor. Combining these two fractions and comparing the new numerator to the old numerator to solve for a, b, and c, we get the following. After you multiply here and rearrange, we get ax squared plus bx squared, that's a plus b times x squared. We have c times x, first degree, we don't have a first degree here by itself. And we have 4 times a, that's a constant. So we compare 2 to this right here. We compare the minus 1 to c, and we compare the 4 to 4a. With that, I have a plus b equals 2, c equals minus 1, which is done, and 4a equals 4. Of course, that means a is 1. So a is 1, c is already negative 1, and when a is 1, b has to be also 1. Let's go back to the problem. Now, this right here will be written this way with these numbers. Here we go. That's my a and b and c. We're going to split this part right here into 2 parts. This is how we do it. Take a look. Imagine this and this with the minus, and you want to combine them. It's the same denominator. So the top part will be 1x minus 1, and that's right there. That's easy to remember. Then after that, we'll see how we're going to handle it. This right here is ln x, absolute value. You need to use u substitution right here. If u equals x to the second plus 4, du will be 2x. A 2 has to show up. A half has to balance it back outside. That's called u substitution. And this part right here from the previous problem or formula, it's tan inverse. So this is x squared plus a squared, where a is 2. That's x squared plus 2 squared. 1 over a, tan inverse x over a. That's this part. Minus outside, and that should do it. Next. Case number 4. In case number 4, if q of x contains a repeated irreducible quadratic factors. The previous one was not repeated. This one is repeated. So we have the following format. Okay, So imagine if ax squared plus bx plus c repeats 2 times or more. So we're gonna keep working on top with linear factors. Let's take an example. As you can see, the q of x here is already factored for us, x times x to the second plus 1 to the second. So this factor is repeated twice. To solve this, we're going to end up with the following. A over x because of this factor, and this right here we're going to write it once, and we're going to write it with second degree. bx plus c, to distinguish we write dx plus e. Again, we do the same game. We combine these with the same denominator. We need a common denominator, which is this part right here. So this one here is done here, covers that. We need an x. This one here we multiply by x to the second plus 1 again to make it second, and we multiply by x. This right here will multiply by x plus x to the second plus 1 to the second. After doing the math, comparing the numerators, this numerator is right here, as you could see. The new numerator is this much. Remember the last one we multiplied by x? That's what's missing. So the top part will be dx plus e multiplied by x. Okay, multiplying and rearranging, it takes time. I'm trying to save you some time. This is what we have. We're going to end up with x to the fourth. This is x to the fourth. To the second, it shows up, which is not shown on the left, but that's fine. Now at least I know the constant, I know the first degree coefficient, and so on. A plus b equals 0. It has to be 0. C equals -1. C equals -1. And this part right here should equal to 2. That's right there. And c plus e should equal to -1. And a should equal to 1. Simplifying, doing the math, if you know c, you know e, and so on. And if you know a, you know b. After that, you will have a and b and go after d. We have a equals 1, b equals -1, c equals -1, d equals 1, and e equals 0. Let's go back to the problem now. Here's the problem. To integrate this, after decomposing, we have the following, with a and b and c and d and e in the problem. This part right here, 1 over x. This part right here, we could split it into 2 parts, just like before. X over x squared plus 1, plus 1 over x squared plus 1. If you want to distribute the minus sign to both, it shows here and it shows right here. And for now, I'm leaving this right there. Using u substitution right here, x to the second plus 1, you need 2x. So you need to show a half after you integrate, as you could see right there. That is tan inverse, which is x squared plus 1 squared, where a is 1. So 1 over 1, tan inverse x over 1. And this one right here, again, u substitution. You call x to the second plus 1 u. You need a 2 outside. And that will end up the following. With ln. This is just regular u, and this is going to end up ln, because the bottom side is like u, and this one will be du, but missing the 2. That's ln. This one right here, it's u squared plus 1, sorry, x squared plus 1 would be u, that's u to the second. When you bring it to top, becomes u to the power -2. And then you integrate it regularly. That's 1 over ln x, and that should do it. As you can see, I'm trying to save the time from recording by having the notes ready to go over, and I skipped some steps in calculations and long division. Thank you.
Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.